Hi everybody, hope you're all doing well. So we're just before we get started on part 2 of our signal generator restoration. Just want to share with you a couple of thoughts about it. I purposely reverse engineered the original circuit and we made a schematic, as you remember in the last video. And when I reassembled it, I tried to keep the component values as close to the original as possible so we can measure what it looks like, what the voltages are and how it performs, and then went through and modified it to correct any of the errors that we had. Now if you recall, I think I have it down here, let me grab it. This thing originally had this old transformer in there, and this is out of an old, I would say probably 1930s radio. And the filaments, the filament windings for the rectifier and for the other tubes were not correct for what this thing was designed. And what I mean by that is the rectifier tube was a 5Y3 requiring a 5-volt filament winding, and this only had like a 2-volt or 3-volt, something like that. And all of the other tubes, the 6SJ7 and the 6C4, they require, and the 6K6, all three of those required a 6.3 volt filament winding, and this one only had a 4 volt or something like that, wasn't it? 4.9 volt, 5 volt. So the filaments were running very cool. They were not running at the proper temperature. That causes all kinds of problems with how the tube is going to perform. In addition, the voltage on the high voltage winding was way too high. And I think they kind of offset one another by doing that. And I think whoever changed this transformer at the time, because this is a modification, this is not how it came from the factory. This was heavily modified. But I think some of the values of the components were changed to get it to work. Now, when I went ahead and replaced the transformer with a more suitable one, those values you're going to find out are not going to be correct, and we're going to have to modify them. And so we're going to build this out, and then I'm going to go in and take some measurements. We're going to calculate some of the things, and then we're going to find out if we're where we need to be or not. And if we're not where we need to be with our voltages or whatever, then we're going to modify the components, the values of the components, to make it work. And that's how we're going to work our way through this. Now, this is not exactly how you would design something from the ground up, but something that has been changed, or when you make a change in something, this is a good practice, and that's why I'm saying I'm enjoying this project a lot, to go through the exercise of figuring out what changes you need to make the circuit work properly. So if that sounds interesting to you, stay tuned, and that's what part 2 is going to be all about. And hopefully by the end of this part, we will have a mostly working circuit. And I don't know that I'll get to building out the probe or anything, because that's going to kind of be a project in and of itself. So sit back and enjoy, and let's get started. Well, I've begun putting together the chassis, and we're going to start building the power supply. But before we do that, let's go over a couple of notes here about this schematic that we drew out on the last video. Now, if you recall, the rectifier tube had been replaced, at least I think it had been, because if you look at the next model after this Model 200, which was the Model 201A, this is the closest schematic I could find, they had a power transformer that only had a 6.3 volt winding, and they were using a 6X5 rectifier. And this one here had been modified with that other transformer, and they had wired it up to a 5Y3. Now, a 5Y3 is a octal version of the old Type 80 rectifier tube. And it's not a really efficient tube. It has about a 60 volt drop between the anode and the cathode. And what that means is that whatever the voltage is across here, you're going to subtract almost 60 volts, somewhere around there, to what you're going to have usable voltage on the output. So with that voltage drop, that actually comes into play when you choose your power transformer and everything. Remember, this circuit isn't designed to run on very high voltages, and the old transformer that they used in there, if you remember, it was going to output some pretty high voltage, and even with that 60 volt drop, it would have been pretty high. But since it had a low filament winding, in other words, it didn't have a 5 volt winding, it only had, what was it, like 2.9 volts, if you recall. Running this tube a lot cooler would make it less efficient, so there was probably even a worse voltage drop in there, who knows. Regardless, we're going to put the correct transformer in. It's going to be with that 60 volt drop, with the 5Y3, we should have somewhere in the upper 200s, just under 300 volts, which is a good place to be, because you really don't want to put much above in that 200 to 250 volt range on these tubes, the way they're going to be operating. So that's one thing. The other thing was the 6C4. I don't know if that's originally the tube that was used for the probe on the Model 200. Now, looking at this socket and looking at these wires, they look somewhat like it was a factory thing, but we just don't know. And that being said, the later model, they changed to a 6AT6 or a 6AQ6. And as we said in the last video, these are more like RF tubes that you would see in a radio, like an All-American 5 radio or something like that. And they actually have diode elements in them as well that aren't being used in this tube. And this is just set up to be a diode itself, essentially. This is called, I believe, called a grid leak detector circuit. Anyway, we are going to recreate this circuit somewhat. I'm going to keep it pretty faithful to this, but there are some changes that we're going to have to make. Number one is the transformer itself. And because of that transformer, we may have to mess around with our power supply resistors a little bit. We may have to change the cathode bias resistor for the output tube, and we may even put a bypass capacitor, we'll see, as well. So a few different things like this. The probe tip, I don't know what value of isolation capacitor they used on this, because the capacitor was missing. Once again, if you remember, you can see the stump where it was cut off, and it probably went to a capacitor, which then went to the probe tip. I don't know. But we're going to start with a ceramic 470 picofarad capacitor, but we may have to change that. We'll see. And a 6C4 doesn't have the diode elements either. In other words, it's not designed to be an oscillator / detector tube all in one, like a mixer tube. Those other ones were more used for like mixers or different stages like that in radios. So this should work. I don't see why it wouldn't work. So we're just going to rebuild this with those couple of changes. We're going to test it, see where we are, and then we'll make changes as we go along. So this part of the video, part 2, we're going to just get this built, and then we'll test it. The last part we'll actually refine everything, and then we're going to eventually have to build a new probe housing and so forth for the RF probe. So far, the only things that I've done is I mounted the power transformer, and I mounted our cleaned off tube sockets and the ground lugs that were on there originally. Cleaned off this terminal. We could do a little more cleaning on it yet. I'll get that finished. And then I installed one of these adapter caps. Now, one thing about a 5Y3, if you look at this at the data sheets on that, the highest value of capacitor that you can place directly on the output of the filament here, of the cathode, is 20 microfarads. Anything bigger than that, the inrush current could damage the tube, so we have to limit that. And indeed, this was a 20 microfarad originally. It's probably still good, I don't know, but we decided to put something else in there. And looking at this 6X5, it's similar. The 6X5 runs on 6 volts instead of 5 volts, or it runs on the 6.3 volts, and it is an indirectly heated rectifier, meaning it has an actual output that is it has an actual cathode element instead of just using the filament as the cathode. I believe on the 5Y3 it's direct. In other words, there is no cathode element in there. So this is going to turn on really fast. It's going to heat up and begin conducting very quickly, whereas the 6X4 or 6X5 would have a little bit of a delay because the filament actually has to heat up the cathode. I'm not going to really get a whole lot into how those work, but that's one of the differences. The 6X5 probably has a little bit lower voltage drop, probably closer to 50 volts instead of 60, but again, it might even be as low as 40. I don't think it's any lower than that, but it's still got a fairly good voltage drop on it, so it should be a similar tube, other than the direct versus indirect heated cathode. So anyway, we're going to get that wired up, and what I've done is we have 3 10 microfarad 450 volt caps. 2 of them are going to get wired in parallel to be our 20 microfarads, and then you'll have your dropping resistor and go to our next 10 microfarad, and then we will have our second dropping resistor, and we're going to use an axial 10 microfarad 450 volt for the last stage. So let's get started on that. Okay, we've made some progress, and basically what we've done so far is we've wired up the power supply. I have that all set, and I need to power it up and test it. I put a new power cord on it. You can see it comes in down here, goes into this terminal strip that I added, and goes out through a fuse block that I added, and then to the power switch, and then back. I put the 2, instead of those old really bad paper caps, I put the proper XY capacitors in there, and then I put a couple of hum balancing resistors to the filament leads, which is right here and here. And then we did our filament string going to these 2 tubes and to the indicator light. I left these 2 lugs open. They'll go to the filament leads that will go out to the 6C4 in the probe. And then the 5 volt leads go to the 5Y3 rectifier. We have our center tap going to ground, which is the yellow and red stripe. We have the 2 red wires, which are your outside leads of your high voltage winding, going to the pins of the rectifier. Now, I don't have any of the tubes fitted right now. I do have the dropping resistors all in, how they were according to our schematic, and the capacitors are all in. So this should be ready to apply some initial power. So the first thing I'm going to do is bring the meter over here, and I will move this over a little bit to make it a little easier to see, just like so. I'm going to go to AC volts because we're not going to put the rectifier in there yet, because I'm really more interested in seeing all the AC voltages. So the first thing we're going to do is we're going to look at our filament leads. So we're going to go to the filament, and this is our 6.3 volt line. All right, move that so we can see it. Let me turn on the, Isolation transformer. I'll plug this in. We still have our current limiting bulb in there. And let's turn this on and see what we get. And there's your 6.3 volts AC. So that's good, so I'll shut it back off. I'll take the leads and I'll move them over to our 5 volt leads. Just like so. Turn it on. 5.2, that's good. Remember, this is unloaded voltage. There's no load on the transformer or on the windings yet. And then last but not least, I want to go to our ground lead. So here's a ground right here. I know some of you people get worked up about the lead color. So there, I'll put the black lead on ground. Doesn't matter because it's AC. Let's go to one side. And we should see our, what was it, 300 or 265 volts or something. Okay, 269, 270. Our mains voltage is a little high tonight, I see, into the house. And 270. Okay, so all of our voltages are there. So now let's do a little bit of calculating before we try putting in our rectifier tube. Okay, remember, this was our old transformer. The new transformer that's in there now, we're reading 200, what did I say, 270 volts. And that's from so that's what we have. Now remember, the peak, that's the RMS. The peak voltage is going to be 1.414 times that. So we're going to take 270 volts times 1.414. That's going to give us 381 volts. Okay? Almost 382. So that's going to give us 382 peak voltages. All right, so when it gets rectified and charges the capacitor with no load on it, you're going to get about 382 volts. But if you remember, when we looked it up, okay, yes, V drop is going to be about 60 volts roughly. So if you take that 60 volts, subtract it from the 381, we should have about 321, 322 volts to the capacitors. So let's say 322 is what we're going to predict. Okay, 322 DC. So when I apply power to this and put the rectifier tube in, this first capacitor that you see right here, our B plus, should be about 322 volts DC with no load on it. All right, that'll be the peak that it'll get to, and then when you start loading it down, that'll drop a little bit. But for right now, that's what we should have. Now, we're going to connect to ground, and the chassis is ground, so you can connect it anywhere. We'll connect it over here. And then you can see off of this one filament, this is your cathode. So this red wire here, see it going across here, that is your B plus. So if I go here, once I turn this on, I should see somewhere around 322 volts. Okay, and what you're seeing here, this 2.5 volts, that's the dielectric absorption of the capacitor that's actually causing it to charge without any without any voltage being applied to it. We talked about that in other videos. All right, let's turn this on and let's see if the math is correct or if I'm not correct. And it would help if I plug this tube in first, wouldn't it? So let's put that in. All right, there we go. Put this back in here. Okay, let's turn it on. And you can see as this tube heats up very quickly. Okay, and we're off a good bit. I said 322 volts. I'm quite off. So you can see even with that little bit, with the other capacitors on and everything like that, you can see it's climbing up a little bit. And it could be that these capacitors are new and they just need to be formed a little bit. That's entirely possible. Could also be that this rectifier tube is a little bit weak and it has a little bit higher voltage drop than it should. And I'm looking at my dim bulb, and it is drawing a little bit of current. Okay, Tony had to have that idiot moment. So if you noticed, our voltage didn't come up to where we thought it should be. And the bulb started drawing a little bit of current, which I expected because of the filament of the 5Y3, but it shouldn't have been that much. So I reached around and touched the capacitor and found one of these 3 caps was really warm. So was the cap defective? Well, after closer inspection, I'll show you, and then you can tell me if you can see the problem. Can you see it? That right here is supposed to be a 10 at 450. But look, it's actually a 47 at 160, and I don't know how that even got into the bin with my 10 at 450s. And laying next to it, it must have been laying on the bench, because look at this. This was laying on my bench, 10 at 450. And look how close they are. I just didn't pay attention. So that was my mistake. So I have to remove this capacitor, and I have to put that correct one in there, and then that'll solve that problem. Let's do our test once again. Okay, we have removed the offending capacitor and replaced it with the correct capacitor. Hey, it's not a Tony video if we don't make a mistake, huh? All right, let's turn it on and see if it explodes or if it works. Look at that. What did we say, 322? We're actually going above that now. That's more like what I expect. So there's a little bit less drop across that 5Y3 than I expected, which is good. Now, of course, when we put a load across that, it's going to be a lot different. And that's how it should look. And the light bulb is not glowing at all now. So if you look over there at the bulb, it's completely dim. Right over here, you can see it. That's what we would expect. Okay? And as those caps form up and settle in, that'll go up a wee little bit. And then as we put a load on it, that'll draw it back down. So let's shut power off. And we'll unplug. You can see. And then we will go ahead and, again, we'll use our discharge wand, or our stinger cable as I call it. And we'll just take that down. We will touch all the capacitors. And there we go. And we're safe. Now this is just a prime example as to why you always want to bring up something that you're working on like this on a dim bulb tester. If this would have shorted, what would have happened is it would have caused excessive current on that rectifier tube and on the power transformer. But because we had a 40-watt light bulb in series with it, that 40-watt bulb would have seriously limited the current to the point where, as long as that bulb lit up bright, first of all, the bright light is an indicator of a short, so you would shut the power off right away. And second of all, that would hold it long enough that you could shut the power off before there's enough overload to actually damage the tube or the transformer. So because we did that, because I had that on there, there was no harm done other than the capacitor got warm and we could observe that light starting to get brighter and notice that there was something that just didn't look right. So just a recommendation, or at least what I do, I always bring everything up like this on a dim bulb for that very reason. It saved my bacon this time, didn't it? Okay, back on this signal tracer. And what we're going to work on now is we are going to work on the amplifier section. So we finished the power supply, and we're going to wire up the amplifier and test it. Since this is a capacitor coupled amplifier, we can do this. We can build each stage, you know, from the power supply and work back and test each stage as we go along, because this section here really doesn't affect this section here other than, you know, whatever current draw it puts on the power supply at idle. But other than that, this should just work. So we're going to get our components, and that 470 is just a preliminary number because we really need to see where this thing biases with the new power supply. Remember, we replaced this transformer and everything, so all of our voltages are going to be a little bit different. So without a doubt, we'll have to change our cathode bias on this a little bit until it's correct. So let's get started, and we'll do a little soldering chat while we do this. Okay, this should be relatively simple because we already have the output transformer wired in, and it goes over to the B+. So we can see here's our B+ going into pin 3. Here's the wire going into pin 3. Am I on the correct pin? Let's see, pins 1, 2, 3. Of course, it's not the right pin. All right, Tony, what's wrong with you? So, yeah, I tacked that on there real quick when I was getting things put together. That's why you got to check your work, you know. You make mistakes. Really, it's not ideal, like I do, to, you know, just work on this in between free moments. You know, you come down here and spend 15 minutes and then, you know, it's not a good thing to do that because you end up making mistakes like this. And, you know, it's just the way it is. But I just don't have the time to spend continuous, and you have to kind of try to remember where you left off. And if you get in too much of a hurry to do something, it's very easy to make little mistakes. So it's even more important whenever you're building something over a course of time that you just always check your work over and over again, because you never know, like that, when you make a mistake. And like when I put that wrong size of capacitor in the power supply. And again, when we go to test this, we will also keep it connected to the dim bulb tester. Just good practices when you're testing, because it's pretty easy to make mistakes along the way. Everybody does it, and especially the busier you get and the more distracted you get, you know, when you're not working continuously, very easy to make a mistake. Sometimes when you really get into a groove working on something, you can work pretty flawlessly, but again, not always. So what that did was, when we had this connected there, that's actually the screen grid of the 6K6, and we wanted to connect it to the plate. Now the screen grid is going to get this wire here, and that goes to our screen supply, which is, if you look here, after this 2K. So you have your B+, you have a 2K resistor, and then your screen resistor going over there. Again, not all of these things are perfect. We may have to fiddle with some of these values a little bit. But I want to reproduce what the original owner did here, because obviously this thing must have had a transformer fail or something on it, and whoever owned it repaired it, you know, rebuilt it a little bit and made some modifications. So I'm kind of curious to see how this works with the original mods that were done to it by whoever I'm assuming the owner did this. And apparently he was as I said, in an earlier time, was a repair shop. He had quite a bit of equipment. Some of it, I mean, it was all very old stuff. I mean, so probably he was big into this stuff in the, in the 1940s and 50s or whatever, because most of that equipment was from 40s, 50s, maybe into the early 60s. Nothing was really newer than that. So it must have been someone from that era, which is pretty cool. Like I said, my cousin worked on these things in that era as well, and he just retired from all of this. And he did this for years and years, and he has had quite the collection of equipment. He still has some stuff, but he got rid of some things, and some of it's buried, in the basement or in the old shop or whatever. One day we hope to go through it and sort through some of those things. But, he and his son have both invited me over to do that. But I don't get over there to visit as often as I used to. Life gets busy, I'll tell you. It's kind of the way it is. When you're young, enjoy the time that you have. That's all I can say, because it goes by quickly. And you really look back and enjoy the times that you spend with your friends and your family and your colleagues and things like that. So, okay. So now we have that in there. And again, I'm not doing the neatest work on earth. Right now, we can later on, we can clean some of this up once everything's in place. But for now, we just want to get it loosely put in where we're going to put it. Now we want our grid leak resistor, and a lot of times you don't necessarily want to call this a grid leak resistor, but that's the common name that people will call it by. There's a lot of terminology. Anybody who's just getting into electronics, you'll find out that there's a lot of terminology that's loosely used out there, and it's not technically correct, but it's just generally used and accepted. And every time I use terms like that, I will invariably get somebody, usually someone who's been at it for a while, who will comment and say, that is not the correct term for that. And that person is absolutely correct. I mean, I just got a comment the other day when I did that restoration of the Yamaha CR820. The last video I did on it was the alignment of the tuner. When we got to the FM section, right in the service manual itself, it said discriminator alignment. And I also called it the discriminator circuit. And one of you viewers came on and said, hey, it's not a discriminator, that's a ratio detector. Discriminators aren't used in tuners, in FM tuners. And I said, whoa. I commented back, I said, if they're not used on FM tuners, where are they used, And he answered back, he said, well, they're used in old FM radios, but modern, analog FM tuners use a ratio detector. And he's correct. I mean, that's not wrong at all. The term discriminator comes from one of the early detector circuits called the Foster-Seeley discriminator. And one of the big differences between it and between the ratio detector is they both use two diodes to detect the modulation or the audio, on your carrier, your IF carrier in this case. And in the original Foster-Seeley circuit, both of the diodes were facing the same direction, the polarity, But in a ratio detector, one diode is facing this way and the other diode is facing this way. And it's very similar circuitry with a couple of differences like that. And most FM detector circuits, you'll hear people use the term discriminator from that original term. And anybody in the industry will immediately understand what you're talking about when you say that. But technically, that's not correct. You know, there are more accurate terms you can use when you're referring to these things. That's one example. There's quite a few things. You know, when you start getting into decibel readings, for instance, the most confusing one, at least to me, is dBu, or decibel, or dB mu, which is a lowercase u with a little tail on it. That's the Greek letter mu. Again, that is a term that can mean several things depending on who you're talking to, because there is the dB with reference to a microvolt, which is the same as dB lowercase uv. Okay, and then it's also, and that's not the correct terminology, believe it or not. It is not. There is also dB lowercase u, which means a field strength, okay, with reference to 1 microvolt per meter. Okay, so dBu meaning field strength with reference to 1 microvolt per meter. And there's also, I've seen the dBu also used as dB units, which is audio units, which is a measurement of audio level. And you see that in the audio industry. And usually that's with the capital U, but not always. And I guess the point that I'm making is that a lot of these things, you know what, I'm not going to put this one in permanently. I'm just going to tack it real quick. A lot of these things, people will kind of interchangeably use some of these terms, and it's not really correct, but most people who work with these things understand what you're saying. And therefore, you know, they get away with saying it incorrectly. And I guess the point that I'm making is that you kind of have to learn some of these things, because once again, when you hear these terms, they may mislead you. And I think that's a very serious point of frustration. And I catch myself doing it a lot. And, you know, I've come to learn a lot of people watch my videos trying to learn some of this stuff who genuinely are still learning. And instead of looking at it as entertainment, they're actually looking at it as education, which is kind of scary when you look to what I'm saying as education. But nevertheless, yeah, I do need to be a little more careful with that. We all do on videos when we do this, because, yeah, it's really easy to mislead somebody. All right, so we have this wired up. We're at a point right now that we could probably power this up and measure and see just what our bias is on this. So we'll clip right across here, and we'll look at the voltage drop. We're just going to see how many volts we're just going to see across this. So we're going to put our rectifier tube, and here is, I didn't even test this tube. I'm assuming it's good, but maybe it's not. Who knows? We're going to use our dim bulb, and if something goes wrong, well, hopefully it'll save our life, huh? So there we go. Let's turn the isolation transformer on, plug this in, and let's get our stinger cable out, because we definitely are going to want to discharge this thing when we're done. All right, power on. And we're now getting a little more glow on the bulb because I have 2 filaments lit up now. And let's see. So we got about, and that bulb's lighting up, so I think we're drawing a little too much current. So we're running about 9 volts. I'm going to turn that off for the moment. And the bulb is limiting it, so it would go higher if I turn that bulb off. All right, let's do some math. So we have 9 volts on the cathode, and our B plus voltage, okay, we'll look at that, is only 174 volts because of the dim bulb. Okay, so 174 volts on the plate. All right, I'm going to shut this off, and that's enough information for us to find out where we stand. Okay, just doing a little bit of math here. If we have 174 volts on the plate, we have 9 volts on the cathode. That means we have 165 volts from plate to cathode on the tube. And if we have 9 volts on the cathode across a 470 ohm resistor to ground, that would give us 19 milliamps. Okay, because I equals V divided by R, or E divided by R. And so we have 19 milliamps. If we take that 19 milliamps times 165 volts, which is your plate to cathode, that means the tube is dissipating 3 watts right now. Okay, just looking real quick at our Class A amplifier, because that's what this is. This is going to be operating at Class A. And it's saying that what we should have is, of course, we have a reading for 100 volts and for 250. So we're kind of in between here a little bit. And you can see so we're going to be a little bit less than the 250 and more than the 100. And if you look, if we have 250 volts on the plate and 250 volts on the grid, which we don't. We have a little bit lower voltage than that, so that's going to change that a little bit. Our zero signal plate current at 250 volts should be around 32 milliamps, and if you remember, we're running at 16. We're running at, or 19 milliamps, and that's only at 165 volts. So we're very, very running it very cool right now. Okay, I've got this I think I got this right where I want it now, but we're going to have to do a couple things to finalize everything. As it sits right now, remember, this tube is not done yet. We haven't wired it. And if you notice, in the circuit that we originally had here, the B plus that goes up to this tube also is being fed, is feeding the B plus that goes to our screen grid. Now remember, we want our screen grid to be a little bit below our plate. And right now, if we turn this on, okay, if we look at our plate voltage, wait till it starts to conduct. About 321 volts. And if we measure the screen grid, it's 327. So it's actually several volts higher. That's not good. That's not what we want. And that is because, let's turn this off for a minute. That is because right now, without any of this circuitry being in here, there's nothing. You have this dropping resistor right here, this 2K at 7 watts, and it's not doing anything. It can't drop anything. You have this big capacitor, 10 microfarads, and you're not drawing any current. The screen grid current is extremely low on this. So it's not enough to really cause this resistor to operate properly. So in order to simulate that, what we're going to do is, I'm just going to put a, what did I put in there? A 68K resistor right in there. And let me just make sure this is drained. I'm sure it is, but we're going to just make sure. And I'm going to tack this across this line right here. So we're going to put a 68K resistor from here to ground. And that's going to draw just a few milliamps is all. But it's just going to be enough to, you know, to bring that kind of where it's going to be when everything's wired up. All right. Hopefully that, yep, that's in there. Okay, let's turn this on. Again, when you're building a tube amplifier, you have to remember that everything has to work when everything is all wired up. When you have parts of the circuit disabled, voltages aren't going to be what they should be because these are unregulated power supplies. They're all dependent upon load. So if you change the load that the amplifier is going to operate at, you're going to change the current and voltage and all kinds of things because these are resistive droppers. Okay, so now we'll measure our plate once again. It's 313 volts. And I'm going to write that down, about 313. Okay, so 313. And now our screen voltage is 311. So it's just a little bit below, and that's what we want. Okay? And if we measure our cathode, it's 31.2. 31.2. And if we calculate, and we have about 0.0156, which is 15.6 milliamps. Okay. If we take our 313 minus 31.2, you have 281.8, times that by our 0.0156, and it's idling at about 4.39 watts. Okay, for Class A. And if we go back to our book, remember we're operating right now at about 313 volts. This thing is at 315 volts. Now, of course, they want your screen grid to be 250. I have it a lot higher, obviously. And again, this is for grid bias or fixed bias. And 4.5 watts is what they're calling for. We're at 4.39. I think we're good. This is going to be just fine. So this is the combination that we want. We want a 2K cathode resistor, and we want to make sure we have about between 3 and 4 milliamps on this side of that 2K dropping resistor. And if we don't have that, we're going to trim it with one of these resistors. We're going to put something on there just to give us a little bit of something for that resistor to work against. If not, we may have to change this resistor. There's a couple things we can do. It's a balancing act, and this is what happens when you're designing vacuum tube gear, because everything is dependent on everything else because everything's unregulated. You have unregulated power supplies, and you have resistive droppers for your power supplies, so everything is going to be dependent on how much current you draw, and that's going to determine what voltage you're going to have across that resistor and so forth. So I think this is where we're going to want to be. And again, we can fine-tune it after we get the preamp stage done. Okay, now that we have everything where we want it, let's just do one test now to make sure that this thing gets sound. I have a coupling capacitor on this little signal generator, and I'm going to turn this on, and let's see if we get sound. Yep. Perfect. Now, again, this little signal generator only puts out like 3 or 4 volts RMS, and that's going to be a lot less than what this pentode tube is going to drive in there, so it's going to be a lot louder than that, but I think we're good. Okay, we now have the preamp stage completed, and in order to get everything where I want it, I had to make 4 changes to the original design, the way it was when we reverse engineered it. You remember when I told you I went through before disassembling all this and I reverse engineered it, and I made that schematic, and that's right here. We'll look at that in a minute. And I removed that 68K load resistor because now this stage acts as the load, you know, on this side of the resistor. And what we had to do is I had to change a couple of the values of the components. And let me go down to the schematic. It'll make it a little easier. I hope you can see it. So anything that you see blue pen instead of the gray pencil color, those are the changes that I made. For the 6K6, the B plus voltage was a little bit high, you know, for this tube, and that has to do with the transformer. If you remember, the original transformer had a higher voltage by over 100 volts, but it was grossly under voltage on the filaments. So it had a 3-volt filament and a 5-volt filament winding, and you know, putting 3 volts into a 5Y3 filament is not going to allow the tube to conduct properly, just as putting 4.9 volts, unloaded 4.9 volts, into a 6.3 volt filament is not going to allow them to conduct properly. So all of these, I knew these numbers were going to be wrong. So with everything how it is now, I had to increase the cathode bias resistor from a 470 ohm to a 2K, and I showed that in a previous clip here. So that's one change we made. This stage here, the gain stage, the pentode stage, I went from a 2.7K to a 3.3K. That doesn't make a huge difference, but it does make a little difference. All of the rest of it is the same. I didn't change anything. And down here on the B plus, that 2K resistor that was originally in here, and that was the main dropping resistor that gave you your plate voltage for the 6SJ7, and it also gave the screen grid voltage for the 6K6. If you remember, when I measured it, the screen voltage was actually higher than the plate voltage. So what I ended up doing was I increased that to a 12K resistor. So that's a lot. I added 10K of resistance to that there, but that's what it needed to be because of how high our B plus voltage was. We want to stay within the parameters of the tubes. And remember, it doesn't matter if your plate voltage is higher than the rating of the tube. When these are cathode biased like this, the main thing we're concerned about is the voltage potential between the plate and the cathode. That has to be within that safety parameter that they list in the spec sheet. In addition, you don't want to raise this so high that your cathode voltage gets so high. If your filaments are referenced to ground for hum purposes, you don't want a big differential between the ground, which is tied to your filament, and the cathode. Now these bigger tubes are a lot more forgiving of that, but if it starts getting up, you know, over 50 volts or something like that, you probably would want, you're going to have to raise these filaments also. But that wasn't necessary in this. We're well within the parameters. Bringing this down to 12K with the loading of this tube brought everything exactly where we want it. Now I'll show you some of the voltages here in a little bit. And this circuit is working perfectly. So let's power it up and measure some voltages first, and then I'll put some signal to it so you can hear it. Okay, now I have full power on this now. I'm no longer on the dim bulb because everything is working. So we're going to go over here, turn it on, and let's look at the B plus voltage. And you can see it's really high right now. And as the tubes begin to conduct, when they heat up, you see that voltage will drop. Now remember, this tube has a maximum plate voltage of 315 volts. So we're exceeding that if you think about it, but we're not exceeding it, and I'll show you why here in a minute. So right there is about where it's going to stabilize, about 330 volts roughly. So if we go over to our plate, which is, it goes through the audio output transformer winding, and it makes that little scratch because it's picking up the signal. That drops it down to about 328. So we have a little voltage drop across the transformer. If we look at the screen, it should be lower than that. So if our screen is 328 with reference to ground, this should be lower. And you can see it's 243. That's right where we want it. So that's good. Now in addition to that, we want to look at the voltage going into the plate of the 6SJ7, and that's going to be this one right here. And you can see it's very low. But remember, if this is not a 6SJ7 GT, if it's it's just a standard 6SJ7, which is what we have here, so that's good. If we look at the cathode of that, 1.4 volts, and if you look at the control grid, it should be negative with respect to that, and you can see it's sitting at 0 volts right now. Okay, and that could vary a little bit with the volume control when we float that high, and you're picking up the noise from my probe right now. Okay, and then if we look at cathode voltage of the output tube, it's about 28.8 volts. And we have this tube almost exactly in line with the manual. When we look in the tube manual, it's sitting right around just a little over 4 watts, which is where it should be at that voltage. So everything is perfect right now, and we should be able to hear some volume here. And I have the volume turned the whole way up, and there's absolutely no hum, nothing. It's dead silent. But if I touch this, you can hear it. Even this high impedance meter picks up the noise. So I'm going to shut this off for now. I'm going to connect a signal generator, and we're going to just put some audio into it and see how it works. Okay, I have this little signal generator. Let's turn it on, and you can hear, I can run it clear into distortion now because it's so sensitive with barely turning this up. So the amplifier sounds pretty clean, especially for that really old ragtag speaker that's on there. I didn't even change the speaker. And this is going to be a good signal tracer. So it works, which is a good thing. And it's dead silent. With no signal on it, it's dead silent. Now when we're completely done with this, I'll clean up this schematic a little bit, and I'll scan it, and then I'll post it up on Patreon so it can be downloaded from my patrons. I'm going to call this part 2, and when we come back for part 3, we're going to work on this front end here, the attenuation circuit. So this attenuation circuit, we're going to set this all up in the switching, and if I get in everything I need for this, we're going to build the probe. And we're going to build a probe from scratch. This signal tracer will be permanently on my bench. I will rearrange the bench to make a place for it because I think it'll be a really handy piece of test equipment for working on the receivers and tuners and things for chasing signals around. The one ICO 147 is nice too, but those types aren't nearly as sensitive as these. So anyway, this is part 2. Part 3, we'll get into the probe more, and we'll finish this front end and try to clean it up a little bit, and that'll be a wrap for this video. So until then, I wish you all peace, joy, happiness, and good health in your lives, and we'll see you again real soon. And until then, stay well, everybody. Bye-bye.